Okay. A very good day to everyone. Today, our Group 2, which consists of me, Darshana, Divya, EILEEN, and Jasmine, will be presenting about Experiment 7, which is the Torricelli theorem. So I'll be talking about the report summary. The introduction is Torricelli had interest in various aspects of physics and mathematics, and Torricelli's theorem was one of his biggest achievements. The law explains the relation between fluid leaving a hole and the liquid's height in the container. The relationship can be summarized in the following manner. If you had a container filled with fluid with small holes at the bottom of the container, the fluid leaves through the hole with velocity same as it would experience if dropped from the same height to the hole level. If the liquid is dropped from a height h, it would have a velocity v, and this v is the same velocity at which the liquid leaves the hole when the height of fluid h is same as liquid dropped in the container. We also assume that it is an ideal fluid, which means that the liquid is incompressible, non-viscous, and laminar flow. These factors cannot be neglected since same rules cannot be applied to non-fluids as their viscosity and flow may not be the same across the liquid itself. Next. The objectives of our experiment is to verify Torricelli's relationship by comparing measured and theoretical value of velocity. And also to find the relationship between Bernoulli's equation and Torricelli's law. So the summary of our experiment is, in this experiment, we compared the measured and theoretical value of velocity by using the Torricelli's law. We set the cylinder to 3 different heights and measured the velocity. Then the results obtained were compared to the theoretical velocity by using the Torricelli's theorem.
So the next one is the theory part. Torricelli's theorem, also called the Torricelli law, stated the speed of a liquid flowing under the force of gravity out of an opening in a tank is proportional jointly to the square root of the vertical distance h between the liquid surface and the center of the opening to the square root of twice the acceleration caused by gravity 2g. Hence, the equation is v velocity equal to square root of the 2 times gravity times the vertical distance. Next. So the velocity of the fluid coming out of the spout is same as the velocity of a single droplet of fluid that falls from the height of the fluid surface in the container. Water stream from the hole is in horizontal directions, which can be represented by kinematic equation. For this case, the velocity v at any point can be represented by time taken t by the stream to cover a horizontal displacement of water stream ds of the water stream s, or the equations 2. So for the constant acceleration, the equations will become the ds equal to v times the times taken plus 1 over 2 times the gravity times the t squared. And at initial point of velocity equals to 0, then the ds is equal to 1 over 2 times gravity times the t squared. Next. Note that the volume V and volume flow rate of the cylinder can be calculated by using the equation 5. The volume is equal to the area of cylinder times the height of the cylinder times the width. And the mu is equal to the area times the square root of the 2 times gravity times the height times the width. That's all from me.
Okay, nextly is the methodology. Next. So first method is the apparatus was set up according to the 3 different heights of stage. Secondly, the cylindrical tank is filled with different volumes of water. Thirdly, the hole in the cylindrical tank is covered using a finger and water is filled at desired volume. Next is finger is taken off from the cylindrical tank hole. And then the maximum distance reached by the water is marked using clay and the time is recorded at the same time. Lastly, the method 2 to 5 is repeated with different volume of water and different heights of stage.
Okay, so I'll be talking about the raw data analysis of this experiment. Your table should consist of a row for volume of water, L, and then initial water level, H. You'll need to have 3 readings and then find the average. This also applies for maximum water trajectory distance, X, and also time taken for water to drain out. The next 2 columns are water flow rate, Q, which is meter cube per second, and velocity of water, V, meter per second.
So I'll be talking about the results and discussion. Okay, so this the table 5.1.1 showing the result obtained for height from floor to orifice 36.65 cm, and the water flow rate. We have 5 different volume of water, which is 2 liter, 1.75 liter, 1.5, 1.25, and 1 liter. So these are the water flow rate and velocity of water recorded for these 5 types for these 5 different volumes of water. And these are the result for when the height from floor to orifice is 56.45 cm, whereas this one is 476.15 cm. So we are going to the discussion. We are to explain our selection on dependent, independent, and constant variable. So the experiment usually has 3 variables, which are independent, dependent, and constant variable. Dependent variables are the factors in the experiment that need to be tested and evaluated, while independent variables are the things that the conductor can change, whereas constant variables are the variables that preserve the values set by the conductor throughout the experiment. In our experiment, the 3 variables are stated below. For dependent variables is the diameter of the nozzle and height of the fluid. For independent variable is the distance of water jet from nozzle, and for constant variable is the density of fluid. So all these variables are being chosen because they are used to achieve the objective in verifying Torricelli's relationship by comparing measured and theoretical value of velocity. This will be split into 2 sections, which is the effect of height of water on water velocity due to the diameter of hole on water velocity. Next one, we are to clarify on how we can relate the Bernoulli equation with Torricelli law for this case. And we are to show all the derivation and explain each step. So the Torricelli law, as we know, we can derive it from Bernoulli equation, and we can relate the velocity of fluid when it leaves the orifice with the height of fluid above the orifice. The first equation showing the Bernoulli equation, and we are to assume P1 and P2 are 0 since it is at atmospheric pressure, and V1 is also considered 0 because the value is too small to be considered. Z2 is 0 also because it is set at the datum. So by substituting all this value into the Bernoulli equation, we get the second equation, and after rearranging the velocity, we'll get the Torricelli law, which is V2 equals to square root 2gz1. So next, we are to calculate the percentage of relative error for the theoretical and measured values. First of all, these are the three equations that we will use to find the answer. First one, we have theoretical velocity equals to square root 2gh in bracket m over s. And next one, we have measured velocity equals to x square root g
over 2y in bracket m over s, where g is gravitational acceleration, h is initial water level, x is maximum water trajectory distance, and y is height from floor to orifice. And lastly, we have percentage error equation, which is equals to v measured minus v theoretical over v theoretical times 100%. So these are the results calculated and tabulated in the table below. For when the height from a floor to orifice is 0.3665 meter, the total percentage error is 146.553%, and the average percentage error is 29.31%. For when the height from floor to orifice is 0.5645 meter, the total percentage error calculated is 133.09%, and the average percentage error is 26.62%. For when the height from floor to orifice is 0.7615 meter, the total percentage error is 228.79%, and the average percentage error is 45.76 percent. Lastly, we are to state the errors that we obtain in the experiment and the ways to overcome them. Based on the experiment result, there were several errors that affect the outcome of the experiment, since there was a difference in the result between the theoretical velocity and the measured velocity. So the errors are the first one is parallax error, which might occur when taking the reading for the height from the floor to scale because the observer's eyes are not aligned and not perpendicular to the reading scale. Second one, the initial water level and the velocity of the water values might not be accurate as the hole may not be fully covered by the finger, which then will cause the water to flow through the hole. Thirdly is the human error, where the timekeeping is not synchronized and might not be accurately started or stopped. So the preventions for all the errors are to ensure that your eyes are perpendicular to the scale of reading when taking the reading. Second one is to check that all the apparatus are in good condition without any leaking before using. And lastly, to repeat all the readings by 3 times and calculate the average of the reading before calculating percentage error. I'll pass the next person for conclusion.
Okay, nextly is the conclusion. Based on the calculation, the data show an average percentage error of 29.31%, 28.62%, and 45.76% on different heights of orifice from the floor. The percentage error of the result is quite obvious, and we can conclude that some errors have occurred throughout the experiment. We should do some precautions to prevent the errors that will affect the accuracy of the reading. Based on the theory, the velocity of water is directly proportional to the height of the initial water level. However, according to our experimental result, the velocity of the water is increasing while the initial water level is decreasing. The experimental result disobey the theory, hence we assume that some errors have occurred. The experiment should be conducted again and make sure all the possibilities of error are eliminated. Throughout this, we can see the effect of the depth below the surface of the liquid on fluid velocity and comparison of the velocity by using Torricelli theorem against theoretical velocity. Thank you.